In this video, we're just going to spend some time solving a couple non-homogeneous Cauchy Euler equations. And the good thing is, now we have all the theory that we need, right? But we just need to illustrate the process, and we'll do that over with a few examples. So let's take a look at our first example. So number one, say it is x squared y double prime minus 3x y prime plus 3y, and that's equal to 2x to the fourth e to the x. All right, so when we look at the left-hand side here, when we look at this differential operator, we see the Cauchy-Euler pattern, but it's not equal to 0 now. So what do? Well, it's still a linear differential equation, right? It doesn't have constant coefficients all the way across. It doesn't matter. Both superposition principles hold. Method of undetermined coefficients, method of variations of parameter, they all hold. So let's go through the process. So first, we need to find the complementary function. So that's y sub c, and that's when we solve the corresponding homogeneous Cauchy-Euler equation. So the x squared double prime minus 3x y prime plus 3y is equal to 0. So let's write down the auxiliary equation here. It's 1 times m times the quantity m minus 1 minus 3m plus 3, and that's equal to 0. So our standard quadratic equation is m squared. We have a minus m and then a minus 3m, so minus 4m plus 3 is equal to 0. And this one, thankfully, is factorable using integers. So the quantity m minus 3, quantity m minus 1. So we can take our m1 to be 3 and our m2 to be 1, right? And again, if we want to get practice identifying the basis. So the basis in this case is the power function x cubed, and then the power function x to the first power, which we'll just write as x. And therefore, using our first superposition principle, the complementary function is all possible linear combinations of the x cubed and x, not a comma there, a plus sign. So plus c2x, all right? So now we have to find a particular function, again, that when this differential operator is applied to that function, it will produce 2x to the fourth times e to the x. Now, in many instances, because you have these additional non-constant coefficients on the left-hand side, it's often not obvious using like the method of undetermined coefficients what your educated guess should be. So in many of these cases, the non-homogeneous Cauchy-Euler equations, the variations of parameter method is what we're going to use, right? Now, the one thing you really have to be careful of in the Cauchy-Euler is that when you're going to apply the variation of parameters method, you have to make sure that your leading coefficient is 1 before you identify this function as your f of x. So in this case, just for the purposes of correctly identifying f of x, we need to divide the given equation, divide it through by x squared. So that's going to give us y double prime minus 3 over x y prime plus 3 over x squared y, and then that's equal to, and then dividing the right hand side by x squared as well, because we have to do it on both sides of the equation. That's going to give us 2x squared e to the x, right? So this is what we're going to identify as our f of x, right? So let's go ahead now and apply our variations of parameter method. So for y sub p, Let's write down the equations that the derivative of u1 and u2 must satisfy. So u1 prime times y1. So I'm just going to use this function that's listed first in my basis as my y1. So that's x cubed plus u2 prime times y2, which in this case is x. That has to be equal to 0. That's the first equation in that special system that's used to determine u1 prime and u2 prime. The second equation is u1 prime times the derivative of y1, so 3x squared, plus u2 prime times the derivative of y2, which in this case is 1, and then that's equal to the f of x once the equation is written in that form where the leading coefficient is 1. So what I have here in blue, that's the f of x. So it's 2x squared e to the x. All right. All right, so let's go ahead and write down the three determinants. We're going to opt for Cramer's rule. Now, let me just say that I always use Cramer's rule, but this is a linear system, right? It's a system of equations. You can apply a lot of other methods to determine what u1 prime is and u2 prime is. Cramer's rule is just one of several methods that you could use. I just find that because your coefficients are now symbolic as opposed to numeric, Cramer's rule, again, because they're set formulas, it's a little bit easier to work with. So W, or first, which is our Wronskian, our first determinant, is a 2 by 2 determinant with the entries x cubed, x, 3x squared, and 1. Let's go ahead and evaluate that. So what do we have? So this is x cubed minus 3x cubed, and that's going to give us negative 2x cubed, right? And I just want to point out, suppose, maybe we all have the tendency to read, the factors and stuff from left to right, but what if your factorization was switched and you had an x here and then an x cubed here? Then your columns would be switched and your determinant would have it would be a positive 2x cubed. But the nice thing is, because of the fact that we're now going to replace the respective first and second columns to get the other determinants, if you follow the correct pattern, it doesn't matter if you start with a pair of columns that's switched as compared to mine, right? So if however you define your basis and your y1 and y2, just be consistent throughout and you won't have any sign errors, right? So that's our W. Let's get our W1. So that's when we replace the first column with now the column that's on the right side of my system. So I have 0, 2x squared e to the x, and then I have my x and 1. So again, using our 2 by 2 formula, what do we end up with? So it's going to be 0 minus 2x cubed e to the x. So we'll get a negative 2x cubed e to the x. And then finally, let's do our W2. So W2, again, go back to the original Wronskian, replace now the second column with the column 0, 2x cubed e to the, 2x squared e to the x. So we have x cubed, 3x squared, 0, 2x squared e to the x. Again, use our 2 by 2 formula. So what do we end up with? 2x to the 5th e to the x minus 0. So that's that's positive 2x to the 5th e to the x. So right beside here, I'm going to write down, now as soon as I, right beside W1, let's write down what U1 prime is. So that's W1 divided by W. So that works out really nicely because we end up having negative 2x cubed e to the x divided by negative 2x cubed. So that just leaves us with e to the x. So u1 is going to be easy to find. Let's see, u2 prime is w2 over w. So that is 2x to the fifth times e to the x over negative 2x cubed. And then let's see, so this one, so we're going to have a negative sign, and then negative x squared e to the x. So this one will require, if you think about it, what method of integration should we use? I'll let you think about it for a bit. So let's go ahead and write down. So u1 is the integral of e to the x dx, and all we want is one specific function u1 that satisfies this, so we don't need our plus c here. The plus c will come up, well, the plus c is actually already incorporated in our complementary function, right? The particular function will never have any arbitrary constants, at least not in this context, right? So that's u1, and then u2, we now have to integrate negative x squared e to the x dx. So this requires integration by parts. Did you remember that? Good. So I'm going to use my table method. So I'll have my u, my dv, and of course I'll choose my polynomial as my u, because I know eventually, after repeated differentiation, I'll get 0. So let's see, we'll have negative 2x, negative 2, 0, and then we repeatedly integrate e to the x, but that's equally easy. And then we do our products. So each of these is a uv. Technically, we're supposed to multiply and integrate that product, but we don't have to since that product is 0. And then lastly, remember to alternate the signs. All right. So we can just look at our table and write down what the antiderivative is of negative x squared e to the x. So we'll have a negative x squared e to the x, and then a plus 2x e to the x, and then a minus 2 e to the x. Again, for the purposes of this problem, we take our constants of integration to be 0, right? So therefore, our particular function is u1 times y1. Well, what was my y1? That was x cubed, plus u2, which is the quantity negative x squared e to the x, plus 2x e to the x minus 2 e to the x times u2. What was u2? That was the function x, right? So if we take a look, it looks like this will simplify a little bit, because we're going to have an e to the x times x cubed term there. And when I distribute the x, and with this negative, I'll have a negative x cubed e to the x. So those will go away, and then we'll have these two remaining terms, right? So we'll have, what's that, plus 2x squared e to the x minus 2x e to the x. There we go. So when it's all said and done, I mean, it's not too strange of a particular function, but again, it's not something that we would have just guessed looking at what's on the right hand side, right, of our equation. Now, if you're good with patterns, I'm not saying the method of undetermined coefficients won't work, but for the Cauchy Euler equations, it's not quite as systematic as how do you choose the y sub p, right? With the method of variation of parameters, you don't have to choose. You don't have to essentially think, okay, what should I guess, right? You just follow this particular process. So there's y sub p and our general solution. So, and y, well, how do we find y? Again, our second principle of superposition, that holds. So it's y sub c plus y sub p. Now y sub c was our c1 x cubed plus c2 x. And then here's our y sub p. So plus 2x squared e to the x minus 2x e to the x, right? So there you go. Pretty good example. I mean, the only part where it, we had to really dive a little bit deeper into the calculus was our integration by parts. But by now we should be, pretty good, right? If not great at things like integration by parts. Let's do another example of this. So this is our second example. And let's take a look at this one. It's a simpler looking equation. We have x, let's see, yeah, x times y double prime minus 4y prime is equal to x to the fourth, right? Now, when you look at this, on the surface, you might be, well, that doesn't, the left-hand side doesn't look like Cauchy Euler because the power of x doesn't fit the order of the derivative. So like here, x is written to the first power, y is differentiated twice. The same thing here. So it's like there's a power of x or a factor of x missing. So since this is not quite Cauchy Euler because a factor of x is missing, well, what can we do? Well, we can multiply both sides by x, which is kind of interesting. Because in the previous example, and we're going to have to do something similar here, but in order to start the process so that the Cauchy Euler method works, right, we're going to multiply both sides by x, right? So sometimes you might have to, kind of dress up the equation just a little bit. Just got to fix it a little bit. So multiply both sides by x. And then that gives us x squared y double prime plus 4x. Oh, I left out the x, and it's not a plus, it's a minus. So minus 4x y prime, and then this now becomes x to the fifth, right? So now it's Cauchy Euler. It's just that one term here is missing on the left. That's not a problem. So let's start by finding our y sub c. We're going to solve the corresponding homogeneous Cauchy Euler equation. And this auxiliary equation becomes m times m minus 1 minus 4m, and then that's equal to 0. So we end up having m squared minus 5m is equal to 0. Factor out an m, and we're left with m minus 5. So here, again, we're back in case 1. We have two real distinct roots. So our m1 is 0, and m2 is 5. So here's our basis. It is x to the 0, x to the fifth. But remember, again, going back to what assumption we're working on as far as our interval of existence, we're working with the interval x greater than 0. So if x is positive and it's raised to the power 0, then that becomes a 1. So we end up getting a 1 and then an x to the fifth, right? So let's write now what our y sub c is. It's c1 times 1 plus c2 times x to the fifth, which is c1 plus c2 x to the fifth, all right? So now here's kind of not quite the complete circular process, but now that we're going to use variation of parameters to figure out what y sub p is, we have to write our original equation so that it has a leading coefficient of 1. So now if I go back and divide through by x squared, then I'll have y double prime minus 4 over x y prime, and then is equal to x cubed. So it's, again, it's for one part of the process, we multiplied through by x. And this now we have to divide through by x squared just to facilitate the different steps in our process. So that means this is my f of x. All right, so next up, we're going to let's write down the system that our u1 prime and u2 prime functions have to satisfy. So u1 prime times y1, which in this case is just 1, and then plus u2 prime times y2, which in this case is x to the fifth, that has to be equal to 0. And then u1 prime times, now look at this, when I multiply, when I take the derivative of y1, I'll get 0. So that coefficient is going to be 0, and that's fine, right? It's not a problem. We've dealt with systems where we have lots of coefficients of 0, and then we'll have a u2 prime, and the derivative of x to the fifth is 5x to the fourth, and here we put our f of x, which is x cubed. All right. Now, determinant time. So 3 determinants. So w, we will have 1, 0. That's the first column. And then x to the fifth. And then 5x to the fourth. Well, that just works out to be 5x to the fourth minus 0, which is 5x to the fourth. Let's see what our w1 is. So w1 is... now replace the 1, 0 with the column 0 x cubed. And then our second column remains the same. Our determinant calculation gives us 0 minus, now x to the fifth times x cubed. That's x to the eighth. So we have a negative x to the eighth. All right. And then let me do w2 beside it and then calculate the u's below the respective determinants. Right? So then w2, first column is 1, 0. Second column is 0 x cubed. Right? So we end up having just x cubed. Right? So we have 1 times x cubed minus 0. So that's x cubed. So now let's go through and figure out what u1 prime is w1 over w, which is negative x to the eighth over 5x to the fourth. So that's negative 1/5 x to the fourth. Now we like to see this because these are functions that are easy to integrate. And let me write down u2 prime. We can sort of do them in parallel. Then we'll have w2 over w. So we have x cubed over 5x to the fourth. And again, a nice, so this is 1/5 times 1 over x. And again, both of these are relatively easy to integrate. This is going to be we're going to use our power rule for antiderivatives here. So u1 antiderivative of negative 1/5 x to the fourth dx. So that's going to be negative 1 over 25 x to the fifth plus, in this case, we're going to choose our constant to be 0. Then over here, we have to be careful with this. Just remember the 1 over x, that's going to be our natural log. So we have 1/5 times 1 over x dx. Integral of that is going to be 1/5 natural log of x, right? So we have our u1, u2. So that means y sub p is u1 times y1. Now remember, y1 was 1, and then plus our u2, which is negative 1/5 the natural log of x, times y2, which is x to the fifth. So we end up having something pretty interesting. Let's see. So yeah, let's just write it as negative 1 over 25 x to the fifth minus 1/5 x to the fifth. natural log of x, right? So that's our particular function. And so then our general solution. So the general solution is, again, our superposition principle says take our complementary function, which is c1 plus c2 x to the fifth, and now add the complementary function. Okay, well, no, not the complementary function, the particular function. And I think I have an extra negative. Yeah, because it's just 1/5 the natural log of x. There's no negative here. So let's make this a plus. And then, so then it will be c1 plus c2 x to the fifth minus 1/25 x to the fifth plus 1/5 x to the fifth natural log of x. There we go. I don't know where I got that negative from. Maybe I just looked at this negative right above it. So there's our y sub p, there's our general solution, and there ends our examples of solving non-homogeneous Cauchy-Euler equations. See you soon.